Hello. We're going to work with triangles today. And as you can see from the top of the page, we're going to be on test 1, section 3, number 17. I've drawn the picture already, and the first sentence in this question is simply a description of the picture above. So we can just skip over that. We don't need to read it. And we'll start with the second sentence. The lengths represented by AB, EB, BD, and CD on the sketch were determined to be, and then they list a bunch of numbers. At the end, they say respectively, which simply means that the numbers are in the order of the sides listed above. So the first number is 1800 and the first side is AB. So those go together. 1800 is AB. Then we have 1400, and that's EB. And it's super important that you are very careful and accurate in labeling these sides, or you're not going to be able to get the question right. Next is 700, and that is BD. And then finally, we have CD, which is 800. Now, the idea here is, well, actually, let me give you a really excellent tip. We have two triangles. And anytime you have two triangles on the SAT, those triangles will necessarily be similar, no matter what. Now, they'll give you mathematical reasons, and I'll show you what these mathematical reasons are for the similarity. But you don't have to worry about those mathematical reasons, because I'm telling you, I'm giving you the shortcut that if you see two triangles, they will be similar. So let me show you. They say that this angle and that angle are the same. And then they say these two lines intersect at B, and then this angle and this angle, I'll do 2 to distinguish them from the others, are equal because they're vertical angles. Well, if two sets of angles in two triangles are equal, the third angles are also equal. So this one, A, is going to be the same as C. And if we have all of the same angles in two triangles, they are similar. But it doesn't matter because we only care about the sides. So now we have to look at the relationship between the two triangles. And there's one obvious thing I see here. We've got 1400 as on one side, and we have 700 on the other. And these are corresponding sides of the large and the small triangles. So we can see there's a 2-to-1 ratio. So now we're trying to find X here, yeah? And so the corresponding side of X is the 800. And if we have a 2-to-1 ratio, that means that X has to be twice CD, or twice 800. The answer is going to be 1600. Okay. Now, there are a couple of other concepts that I want to share with you in terms of triangles. Let's see, where shall I begin? Okay, well, first of all, let me just draw a line here to separate. Okay, there's just a simple geometry law, right? Geometry is a very visual math. So you always must label everything, right? So if they give you a picture, you label, let's say you would label the sides or the angles, or if it's a circle, you would label the radius or an arc, right? Anything that there is to label, you put it on the picture. Now, sometimes there is not a picture, in which case you draw, right? So you draw the picture. If they just tell you there is a rectangle, you draw the rectangle. If they say the length is 8, you make it 8. If they say the area is 48, you write it down 48. Okay, so everything is labeled, everything goes down on paper. Okay, so that's another point. Now, third point, I'm going to fill up this page, I think, today. And what I want to do is talk about special triangles. And special triangles are definitely on the test. You should expect to see them. And there are multiple special triangles. So the first one, I think I'll begin over here. And the special triangles are always right triangles. So that's the first thing to know. Okay, so the first right triangle that's considered special is the 3, 4, 5 triangle. Now, sometimes the 3, 4, 5 triangle looks like this. It might look like 6 and maybe 10. It's up to you to say, hey, wait a second. This looks like a 3, 4, 5 triangle multiplied by 2. And this is the way I like to notate it. I like to put the 3, 4, 5 in parentheses and say, well, if I multiply it by 2, does that make sense? And then I would just distribute that 2 out to all the numbers, right? So 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10, and we have a 6, an 8, and the 10. This 5 is always the hypotenuse, right? It's always going to be the longest side of the triangle. Okay, so that's the 3, 4, 5. Likewise, very similar to the 3, 4, 5. And you notice we haven't talked about the angles in a 3, 4, 5 triangle because we don't care. We're only concerned with the sides. So there is also a 5, 12, 13 triangle, which also is the type of triangle in which we do not care about the angles, just the sides. So you should know 5, 12, 13. So, for example, if you see something like this and 12, you should not have to figure out the hypotenuse. You should just say, hey, it's 13 because I know the 5, 12, 13. Now listen, the reality is you can figure all of these out by doing the Pythagorean theorem, which you should all know, right? You definitely want to be knowing that. But if you know the 5, 12, 13 and the 3, 4, 5 triangles, you have no math to do. It's really easy. I highly, highly recommend that you know these two. Okay, moving forward, we've got probably the most common triangle, special triangle, is the 30, 60, 90 triangle. So 30, 60, 90 triangle, we actually care about both the angles and the sides. Their accompanying sides, in other words, the sides opposite these angles are 1, root 3, and 2. So the side opposite the 30 is 1. The side opposite 60 is root 3. And the hypotenuse is 2. All right, you should know these. It's going to make your life a lot easier to know them. You could actually see something like, let's say they just give you the 30. You would be able to assume that this is 60, right? If they just give you this, what you would do when you're labeling geometry is you would fill in that 60. And let's say they told you this side was 4. Well, you would realize that it's 1 root 3, 2 multiplied by 4, because when you distribute 4 to the 1, you get side 4. And then to figure out the others, you distribute that 4 over. 4 times root 3 is 4 root 3. 4 times 2 is 8. Okay. And the last triangle is going to be a 45, 45, 90. And the corresponding sides there are 1, 1, root 2. So anytime you see a root 2 in a problem, you should have that automatic association of a 45, 45, 90. If you see a root 3, just circled that, you should have that association that it's a 30, 60, 90 triangle. Okay, I'm going to clear the decks here, and we're going to move on to another concept. This one, I haven't seen that often, but I've seen it sometimes, and I just want to put it out to you, just in case. I want you to have all the tools that you possibly can. We've got 3 parallel lines. This looks like maybe let me just make it look more like a regular parallel line. Okay, and let's say we have a slanted line And we're talking about, let's say this, we're talking about, let me get a color here so you can see. We're talking about here, this line here, and this segment of that purple line is X. And let's say this one is 3X and this one is 5X. Now, if we say that from from here all the way down to here, right? That height, let's say we say that is 18. Here's the rule. This is called the proportional segment theorem. And I don't care if you don't remember the name, okay? It's the concept. It's that typically you don't think of a slanted line as being able to, as being the same as a vertical line. But in this case, it's true because these lines are parallel. Okay, so when you see parallel lines, you can add up the entirety of, let's just get rid of that. Okay, it just goes from here to here, right, like that. You can add up the X and the 3X and the 5X. If we add those, we get 9X. That is going to be equal to the 18. And then we can just divide out the 9, and we get X is 2. So we can say that the X is 2, the 3X is 6, and the 5X is 10. So if they were asking us to solve for X, we get it. If they ask us to solve for this segment, we get it. And if they ask us to solve for the biggest segment, we get that. Okay, so proportional segment theorem, where the slanted line actually equals the length of the vertical line. Okay, that's that. Now, what else do I want to talk to you about? Well, there is an interesting, let's make this the last one. I think this is the last concept here, and this has to do with proportionality, and also when there are two triangles. Okay, so let's say we have this picture, it's a triangle within a triangle, right? And let's say we've got A, B, C. Let's say we've got, let's say this side is 6 and this is 8. And we want to know AC. Okay, that's what we're trying to solve for. We need some more numbers. Let's say this is 18. Okay, now we know that there are two triangles, and where there are two triangles, right? We've got the small one here and then the large one. Where there are two triangles, we know they're similar. Similar is the same thing as proportional. And in this case, we're going to create a proportion. We have the small triangle as proportional to the large triangle. Okay, so, and let's say, okay, no, we'll just leave it like that. Okay, now, what do we have? What numbers can we start to fill in? Well, we have this vertical line here of this vertical leg of the small triangle is 6. And we want to compare that to the vertical leg of the large triangle here. And that's 18. That is going to be equal to some two other sides, right? But we're looking for AC. We're looking for the hypotenuse, right? We're looking for the large triangle. That's going to be our X, right? We'll just put a big X there. And that, I just want to make it clear, that encompasses this whole thing. So when you are labeling, if you just happen to put an X like that, it's going to look like that's the small hypotenuse. Or if you put it up here, it might look, let's say we make that a D, it might look like AD, right? So you want to forget those. You want to do it like this, like make sure that it's very clear that X is the huge hypotenuse. Okay, and then we have to figure out, we need another number here, right? We have to figure out what the hypotenuse, or not the hypotenuse of the small triangle is, DC. Now, if you took to heart what I said before, you would recognize the small triangle as a 3, 4, 5 triangle multiplied by 2, and you would say, oh, that hypotenuse is 10. It's a 6, 8, 10 triangle. Great. So we go like that. Okay, we have small number to large number, small number to large number, and then we can cross multiply. Remember, when you cross multiply, you keep that equal sign. The whole point in cross multiplying is so you can get rid of your fractions. So when you cross multiply, you get 6x equals 180. You divide by 6, and you get x equals 30. AC is 30. I'm not going to make that mistake because when I look back at my picture, I realize, oh, the big hypotenuse is x. Now, if they asked for AD, you would take the big, right? So this is 30 here, the big one. And you would just take the 10 away and you get 20. AD is 20. Okay? All right, that's what I've got for you. You take care. I'll see you next time.